Ok, merci beaucoup d'être ici pour ce dernier séminaire. So I'm going to switch to English now. It's really my great pleasure to introduce to you Professor Tracy Northup. Tracy is a US citizen, but she did her undergraduate studies at Harvard and her PhD in Caltech, so California Institute of Technologies, next to Los Angeles, where she studied with a very famous professor, Jeff Kimball, who was a pioneer with Professor Gerhard Rempe, I would say on the European side, that you met a few weeks ago, of trapping single atoms in cavities. And so Tracy is a major expert in this field of trapping ions in systems and in cavities. She joined then the group of Professor Rainer Blatt in Innsbruck in Austria. Professor Rainer Blatt, I mentioned his work when we discussed ion-based quantum computers. So there is this quantum computing company called Alpine Quantum Technologies in Innsbruck, nearby where you just live. And so Tracy joined there as a postdoc, then as a tenure track, and she became a full professor in 2017. She's leading the activity between, for the interface between a single ion and a photon for quantum network and for scaling both quantum computers and quantum networks. She's a major figure of the Quantum Internet Alliance that I just introduced to you. And she is a board of director of the Cluster of Excellence of the Innsbruck Quantum Austrian Quantum Initiative. Yeah. And she got a decade ago now, the start prize from the Austrian Stein Fund. So I'm very eager, I'm very happy that she accepted to give the last lecture of this series and that she will have the chance to discover her amazing results. Thank you, Tracy.
Pascale, thank you so much for this kind introduction. Thank you for the invitation. It's really a pleasure and an honor to be here. I was so happy when I was sort of thinking about what background the audience would have. I realized I was very lucky to join you at the last lecture for this series because I was looking at what you had seen before. And so I saw that what you've studied since January were all of these topics that I wanted to bring up today. You looked at things like stationary and flying qubits and entanglement and how we measure it in the laboratory. You looked at decoherence and how to generate single photons with atoms, the Hago-Mandel effect, photon and atom-based quantum processors. And so I know that you're not experts on all of these things, and I'll try to remind you about them as we come to see them again. So what I really hope today is that this is a chance for you to see some of these ideas that you saw during these past few months, that you can see them in a particular example. Quantum interfaces are really a great opportunity to put together these different components of quantum technologies. And I think you saw that in the lecture just now that you heard from Pascale, that you sort of bring together these different components about flying photons and stationary qubits and information storage and information transfer. So I'm looking forward to taking a look at them with you. Something else, actually, I saw that you had looked at in these lectures are the DiVincenzo criteria. And I thought that might be a nice place to start. People often think of David DiVincenzo's criteria as for quantum computing. But if you go to his paper, he makes it clear that computing, we should think about this very broadly. I encourage you, by the way, to take a look at his paper if you haven't, because it's very accessible, it's short, it's pretty easy to read, and it's really nice. And so, right, he's thinking about what we need to build a quantum information processor, and he reflects on the fact that quantum information processing is not only about computing, but also about communication. And he gives here some examples that we still believe in today about useful things you could do with quantum communication. And so you've seen these kind of 5 core criteria for a quantum computer. And I think you've also seen these 6th and 7th criteria, but I just wanted to remind you about them here. So he has sort of these extra 6th and 7th criteria that are specifically about quantum communication. The 6th one is about the ability to interconvert stationary and flying qubits. And the 7th one is the ability faithfully to transmit flying qubits between specified locations. And so this is really, these 2 ideas, this is at the heart of what I want to show you today. And I wanted to give a short quote when he's reflecting in his paper on this idea. He says, requirement 6 is the really hard one. And he says, to date, the only theoretical proposal significantly concrete that experiments addressing it have been planned is a scheme produced by Kimball and coworkers. And so at the time when he wrote this in 2000, there was really only one good idea about how to build such a quantum interface. Now, 26 years later, we have some more ideas. We've come quite far, but it's still really hard. This is still really challenging, but it makes it a really fun scientific topic to work on. So what I would like to tell you about today, I'd like to look at one example of one of these quantum interfaces. And to be very concrete, so let me show you. Here's a map of our university campus where my laboratory is. There are 2 buildings on that campus. In this building here, that's where my laboratory is, and we have a single ion trapped in an ion trap in that building. This is an experiment that I did together with my colleague's research group. At the time, he had an experiment over here in another building where he had another ion trapped in a different setup. And so the story today is going to be about how we can entangle these 2 ions in these different buildings. And these are ions that have never seen each other. They've never been close to each other. They were always in different buildings, but nevertheless, we can prepare them in an entangled state. That is, we can compare them in some state where we can't describe them individually. And so the key enabling steps here, from a matter point of view, we have these trapped atomic ions. And as you've learned about, in particular today, this idea about quantum memories as a way to store information, and also information processors, that we can think of these ions both as memories and as processing tools for quantum information. And then we have light, which enables us to bridge the gap between these distant objects using single photons. And then we need some way to translate back and forth between the light and the atoms. And this, in our experiments, is based on optical cavities, on using 2 mirrors facing one another and bouncing the light back and forth between those 2 mirrors such that they interact with the atoms. So this is an experiment that we did a few years ago. That's what I'll focus on. But I want to kind of keep in mind that we're not the only people doing this. There are many groups around the world. And in particular, people are really now putting these experiments into kind of over long distances and into kind of metropolitan settings. So beautiful work here from Harold Weinfurter's group in Munich, entangling atoms over 33 kilometers of fiber. Here in Hefei, China, work that was using again, actually in a city environment here, sort of it's across the city. And another kind of city example here in the Boston area, Misha Lukin's group here. And all of these are actually 3 different platforms, also different to what I'll tell you about today: single atoms, ensembles of atoms, solid state quantum memories. And so I hope that kind of reflects the fact that, as you've seen for these quantum technologies, there are just really a wide range of, there's a wide range of really interesting and promising technologies that many people are working on. Right, I want to start with the question today about what a quantum internet is and why would we want one. Then we'll take a look specifically about trapped ions and how we can use them for future quantum networks for a future quantum internet. And then I'll tell you about the experiment I've already summarized, entangling two ions across our university campus in Austria. And finally, I'll look at a little bit about how we could scale up these kind of experiments in the future. Right, so what is the quantum internet? I think this earlier today you already saw some illustrations about quantum networks. This is an illustration that comes from a consortium that you also heard about, this Quantum Internet Alliance, which is a European effort to build quantum networks. So it's a very European-based vision of linking together quantum systems on a scale of a continent, right? And also you can see going across oceans to other countries. And so, right, what do we mean by a quantum internet? The idea is that we want to distribute quantum entanglement here. And we want to distribute it between any 2 points. They could be nearby points, they could be far away points, but we would like to do it efficiently, and we would like to do it faithfully. We don't want to make mistakes. So these kind of glowing orbs, these are supposed to be nodes of our network where we can do local quantum computation, simulation, and sensing. And so you can picture that these are these different nodes, and they're connected by things that look like lightning bolts. And that's supposed to represent that we can distribute quantum states along these quantum channels. And we expect that that's going to be with light. OK, and so we can also sort of be more specific about what these nodes are. We can say if it's sort of an end node of a network, a place where the network, yes, where somebody is trying to perform a network task, then we want the ability to do quantum information processing at those nodes. But in order to bridge such long distances, we might not only need processing nodes, but also nodes that just help us bridge the distance. So little kind of steps along the way, so-called quantum repeaters. And so we can imagine that we will need intermediate nodes specifically dedicated to these quantum repeaters. Right, so why is that all a good idea? It looks pretty complicated. So one major motivation is secure communication. And in particular, right, current encryption methods for communication, we know that they can be broken if there were sufficiently powerful computers. So they're based on the fact that these problems are too hard, that the problems that we're using for encoding are too hard for our current computers to solve. And so this appeal of using quantum key distribution is that this is a method for encryption that offers information theoretic security. That means that even if somebody, a hacker, had unlimited computing resources and time, this security would still be robust. And there's lots of work going on in France on quantum key distribution, also throughout Europe, both academically and commercially. This is one of really the earliest quantum technologies to be commercialized. And so if we want to now distribute quantum keys for encryption over long distances, these kind of entanglement-based networks and quantum repeaters that I described for you, these will now come into the picture. It's not just about communication, it's also about quantum computing, because that meets communication when we think about tasks like doing secure computing in the cloud. And I think that's maybe a familiar idea to all of us. There are plenty of tasks that we can't do on our own laptops or phones or computers, and we kind of send them out into the cloud. And it's the same idea here. We expect that in the future there will only be some small number of, in the near-term future, we don't expect there to be too many quantum computers at first. And so we're expecting that people will be sending tasks to these computers over some distance. And of course, we think that computers in general are going to be more powerful when we link them together. And so a way to boost the computing power of quantum computers will be to link them in clusters. And when we say clusters, that's a kind of a quantum network. Yeah, there are many specific tasks. Some of these are the ones that DiVincenzo mentioned in his article already more than a quarter century ago. Tasks like, for example, clock synchronization or position verification. Right, so yeah, if we want to kind of build a network where we can link entangled states over long distances, what would we want to use for it? What kind of a platform? So let me tell you about these trapped ions that we're using, and I know that you've heard about them already a few lectures ago. And you've also heard, I think, from Anton Broe a few weeks ago about neutral atoms, which share many strengths with trapped ions. So here's a pretty photograph of the kind of a vacuum chamber that we use to confine these trapped ions. So it's basically to remind you or to tell you here that these are experiments. They happen at room temperature, typically. Sometimes people put them into cryogenic temperatures, and we can talk about reasons you might want to do it. But many of these experiments happen at room temperature, but at ultra-high vacuum in this kind of a chamber that's where it has been pumped down to pressures that are actually lower than sort of our local space environment, but not quite as low as deep outer space. So what you see through this window is a little glimpse at an ion trap. And this is a so-called linear Paul trap. It uses 6 different electrodes that are shown here. And we put radio frequency voltages on these electrodes to trap these charged particles. So for these linear Paul traps, it's this radio frequency that's used to confine these atoms in ultra-high vacuum. And once we have the atoms there, we want to do gate operations. You've learned about the Dirac-Zoller gate, for example. And we do those typically with with lasers or microwaves that we use to manipulate the atom's electronic or motional degrees of freedom. I think you saw this picture a few weeks ago to remind you about a Paul trap. So it's about putting voltages on opposing electrodes. So you can see electric fields that are pointing here to the left and here to the right. So from the top and bottom to the left and right. And then those are flipping back and forth very quickly from a configuration where the arrows are pointing to the left and here they're pointing to the right. And so they're flipping back and forth so fast that the particle in the middle can't follow too fast. And the middle is always the sort of the lowest energy place to be, the kind of safe trap place to be. And that's what we refer to as a pseudo-potential. Right? So it results in something that looks like a harmonic oscillator, that looks like a particle just rolling around back and forth in a well. And you can think about all 3 axes, all 3 dimensions for that particle look the same. It's just rolling back and forth. Yeah, 10 electron volts is very deep. We should compare it to the energy of particles in the vacuum chamber that are bouncing around and colliding with it. And those have energies of 1/40th of an electron volt. So it means that collisions with gas are not going to kick these particles out of the trap. The particles stay in the trap for days sometimes, maybe even a week or longer. And they're oscillating around at something like a megahertz frequencies. Yeah. Here are some pictures of these trapped ions. So what are we looking at? We're looking at a camera image where a laser is being used to excite the atoms to an excited state, and a lot of light is being scattered by the atoms. And so we're collecting the light on a camera, and that allows the ions to be localized. So they're separated here by about 5 microns between the ions in this picture. So what you've heard already in this course is that these ions can be used for high fidelity gate operations in a quantum computer. And that means when we're saying high fidelity, we're saying that the errors that you get are really low, among the lowest that you see for all these candidates for quantum computing. And another really strength of these trapped ions is that you can store quantum information in their electronic states for relatively long times with respect to the times of these gate operations. And finally, there's some nice prospects for making these computers bigger and bigger. In particular, the so-called quantum CCD architecture allows you to steer ions around a trap into different zones, for example, computing zones, memory zones, and that can be really helpful. So many of my colleagues around the world are working on these wonderful topics for quantum computing. But again, we're going to focus here on a quantum interface. That is, we're not so interested here today in how we compute with the ions in one location. Instead, we want to connect to different ion computers. So what we want to do is to have an ion in this trap on the left, an ion in a second trap on the right, and build a link between the two traps. How do we do it? There were people who've been thinking about this for several years. This is a proposal here, or it's an illustration about how you would do it. So this is a picture of a single processor, but you can see it might already even have a few different kinds of ions in it. Here, these are ytterbium ions being used for a quantum memory, and also barium ions being used specifically for communication. And then what you see here is these interfaces, some kind of interface that's labeled cavity in parentheses that's carrying quantum information off and out of the picture. And another picture, another theoretical illustration here from Nicolas Sanguard, from Debussy and Christophe Simon was back in 2009, where what you see explicitly is these ions that are getting shuttled here in and out of these little illustrated things are these optical resonators or optical cavities. So one mirror on the left, one mirror on the right, and the photons are bouncing back and forth between them. So the idea is, again, that what you see is that these are quantum processors, and we could link the quantum processors. Each ion in a cavity would allow us to link here ion A with ion B, thereby linking the two processors, and a second processor could be linked to a third here via these two other cavities. That's just a nice concept on paper. So both of these pictures are from proposals. And so let's take a look more carefully about how we would achieve this in a laboratory setting. Right. So I want to show you some pictures to start with. So this is an ion trap now, not just as a schematic, but showing it to you, the photograph from our laboratory here. And so it's not as big as it looks in the picture. It's kind of something that you could hold in your hand. These two, so this is a mirror here, and this is another mirror here on the left and right. And those two mirrors are 2 centimeters apart. So as I've told you, these are electrodes here for confining the ions also below and above. And so that means that the ions are in a line. Actually, it should be vertical, but I just put it this way so you could sort of see it better. This is should be a vertical line here with the ions that will here, if you illuminate them with a laser, they can blink on and off. This is illustrating to you this qubit state, this quantum bit that we're using to identify if the ions are bright or dark. That's the equivalent of 0 and 1 for our quantum computer. So we're saying, okay, we can identify them as 0 if they're, say, dark, and 1 if they're bright. Right, so what do we see? We have the ion trap, then the 2 mirrors. And so you see that the ions are right in the middle of the mirrors. And so that light going back and forth between the mirrors will bump into the ions, will hit the ions. And so if a single photon bounces back and forth between these mirrors, say something like 30,000 times, then it has 30,000 more chances to interact with the ion than it does if it simply goes by in one pass. And so this is how we take advantage of boosting the strength of the interaction between just a single photon of light and a single atomic ion. What else do we see in this picture? So we see some lenses here. And this is because the optical field here from these mirrors is diverging very quickly, and so we need to recollimate them. We also see that this is something that graduate students built in the lab. You see some extra glue and kind of got a little messy here. And this is the way we do experiments in academia, right? We put these things together for the first time. They take months, they take maybe years to build. And then there's a transition to learning how they work, and then figuring out how we can convert them to robust technologies. And so something that's been really fun for my group in the past few years has been to work together with Alpine Quantum Technologies, AQT, as Pascale mentioned. They're a quantum computing company in Innsbruck. And so thinking about how we can now take this academic system and make it much more robust for future technology. And so we have students from my group working with scientists from the company to do that. Okay, so what do? We can trap these ions here, and we can put them between the mirrors. But what do we want to do with them then? Whoops, sorry. So let me first summarize for you on one slide how we can entangle two remote ions, and then we'll look at the parts in depth. So the idea, as I told you, is that this is the setup that I've described to you currently. It lives in this building, we work on it in the basement, or in the ground floor here. Then there's a similar setup here. You can see that also is an ion trap with mirrors. It looks a little bit shinier because here the electrodes were coated with gold, but that was just to make them a bit smoother to avoid the surface being too rough. So they're very much the same setup. In both cases, we trap single atoms, different buildings. It's separated by about 520 meters of optical fiber, about 230 meters in real space. And so what we're going to do in each laboratory, we entangle a single atom with a single photon. The photon is in the infrared. It's at 854 nanometers. So here's the photon from below and the photon from above, or there. And then what we're going to do, so maybe first, a little notation, right? We can say that if we use the zero, the green to encode the ion, and the blue to encode the photon, we can use spin up or spin down, or zeros and ones for this kind of a qubit or a spin encoding. So for example, an entangled state would be that if the ion is in 0, the photon is in 1, and if the ion is in 1, then the photon is in 0. And there's some prefactor alpha or beta that weights those two states. So this would be an example of an ion state entangled with a photon state. What specifically are we entangling? We're entangling the energy of the ion, so it's the outermost electron with the polarization of the photon, right? So those are the photons. It's the polarization of the photon entangled with the electronic state of the ion. And then we send one of the two photons to the other laboratory. So they both essentially go to an intermediate location, but the one on top doesn't have so far to travel, just a couple of meters, and the one on the bottom travels over about 500 meters to reach the other one. So we bring these two photons together, and then we put them on a beam splitter. The role of that beam splitter is to erase information about which photon came from which laboratory. I think that you just saw that in the previous lecture, and so this is a chance to see it in action. And so now the photons come together, we erase the information about which one came from which laboratory, and then we measure both of the photons. And sometimes they have the same polarization, and sometimes they have the opposite polarization. To be more specific, half the time they have the same polarization, half the time they have the opposite polarization. When they have the same polarization, we ignore it and we just try again. When they have opposite polarizations, then we know that we have prepared the ions in an entangled state. So, right, it means that if both photons were in this state here, now we've prepared an ion, so we can prepare an ion in an entangled state, and where we have two ions. And so, right, these are the ions above and below, they're entangled, and we can take some data that tells us that they are in fact entangled, and that gives us information about how entangled they are. Okay, so that was the kind of nutshell summary of everything. And I think there's many open questions here. So how are we entangling these ions with these photons? And what exactly are we doing when we're sending them to this beam splitter and measuring them? And that's what I want to look at a little more deeply on the next slides. So what does it mean to entangle the ions with the photons? So what we have, again, we've got this little ion, and we're putting it between these two mirrors. And what you see in these sort of red structure is supposed to represent the standing wave field of this optical cavity. And so we can write down an atomic level structure for the ion. And so this is now, we're describing the energy levels of the ion. And in a simple version, we can just think about 3 energy levels here. And we're going to start the ion at the bottom in its lowest energy state. And then we can choose lasers that will talk to the ion. And so the blue arrow is a laser like this one here that's on this diagonal coming in from the side. And that will excite the ion almost up here to this excited state, but not quite. What's the red arrow? It's actually not another laser. Instead, it's the field in this cavity. And it's actually nothingness, right? It's an empty cavity. But what we can do, and sort of the wonderfulness of quantum mechanics, is that if we turn on the left laser, this will actually help us pull a photon out of the vacuum and generate a single photon. And this is the process that you've heard about a few weeks ago, how we can use an atom to generate single photons. And here we're doing it specifically in a cavity mode. So we're pulling this photon out of the vacuum. We're generating a single photon with 1 laser and 1 cavity. And we can also, so that the ion then in the process gets transferred from the left side to the right side. And if we want to check where the ion is, we can illuminate it with light. So we can illuminate it with a light field that takes us up to another excited state of that calcium ion. So that is this laser. If the ion is over here on the left state, in this state called S1/2, then the ion goes up and falls back down again. And it does that millions of times a second. We collect the light. This is what it looks like on our camera. And we say we know it was in the state S. On the other hand, if we're over here in this D state, the laser doesn't do anything to the D state. And so when we look on our camera, it's dark. And so this is how we tell whether we're in S or in D. And that gives us this background information that we need. The last step is that we have another laser that lets us actually rotate the ion between these 2 states, S and D. And so if we were doing quantum computing today, we would call these our qubit states, S and D. This is our 0 and 1 for our quantum computing. And if we wanted to do single qubit operations between these 2 states, this is the laser we would use to do that. And here, it's the laser that we can use to analyze whether we generated entanglement. It also lets us do preparation if we want. OK, so what I've described to you here is that not only can we put a single atomic ion between 2 mirrors, but we can use the mirrors to generate 1 photon. Whereas the photon, it's bouncing back and forth between the mirrors until eventually it leaves because it goes through one of the mirrors, and then we can detect it. It's just a single photon. It's not entangled with anything. But I told you we were going to try to entangle the ion with a photon. So let's look now at how we do it. Again, here's that picture of the ion trap coupled to the cavity, just to remind you of what it looks like in the laboratory. So we have a single ion in the middle. And we go back to this picture of generating a single photon. And the idea is that we're just going to double it. So if we have 2 different ways to make a photon, and there's some phase relationship between those 2 ways, there's a well-defined phase relationship. That is, we would say in quantum physics that this is a coherent process. Then we actually entangle the 2 final states. So what I showed you before is that we can go from this S1/2 state to a state here, which we'll just call this one D. But there's actually a couple other states over here along with D. And so here I'm introducing a second state, a second energy level called D prime. And I can use a different laser to make a photon that takes the ion not to D, but to D prime. Why do I need a second laser? Why didn't the first laser take it to D prime? Because the 2 states, D and D prime, they have slightly different energy levels. And that's why this first one, D prime, is high, D is higher than D prime. That's indicating this energy difference. And in order for this photon generation to work, the energy of the laser, the frequency of the laser, has to exactly match the energy that we need. So the first laser, you can see the first blue arrow is a little bit longer. That's telling us that the first laser is mapped to the first state. The second laser is tuned specifically to the second state. And we generate 1 photon on 1 transition that takes us to D, and the other photon that takes us to D prime. Right, so the last step here is that we choose these states of this atom in a specific way so that the two photons have orthogonal polarizations. So they're traveling in the same direction, but their field is oscillating at right angles. And so we would say that this one is horizontally polarized, this one is vertically polarized. And so in fact, yeah, what I've described to you is two pathways. We could either put the photon in a horizontally polarized state and end up in this d electronic state of the ion, or we could put the photon in a vertically polarized state and end up in the d prime state of the ion. And the result is a superposition of these two options. So dH plus d prime v. And in fact, we're going to, we have a 50% probability to do this, and now here comes the phase relationship. It's not just a 50% probability, but there's a relative phase, and so we say that these two things are entangled with each other. So it's pretty simple. We just need to put an ion in our mirrors. We turn on these two lasers, we balance them, and then we should have this photon that is entangled, just one photon, but it's entangled with the ion state. And in fact, that's what we see in the lab. We can demonstrate that we do get one photon that's whose polarization is entangled with the state of the ion. Okay, that was the first step that I told you about. We can know that we can put a single ion in each trap, and we can entangle it with a single photon. But that's all local. That just happens in one lab. And we want to use this in order to entangle two different laboratories. And so the idea is that in this laboratory, we entangle a single photon with a single ion. In the other laboratory, we do the same thing. This is my colleague Ben Lannion, whose research group built up the second experiment here that I'm showing you. And so, right, we have these two buildings. We're very lucky that when the people who built the second building were putting it together, they put together not only one optical fiber connecting the two buildings, but like a whole bundle of optical fibers. So we can, it's pretty easy for us to just link these two labs. The fibers go like through the parking garage, but it turns out that's fine. That's okay for us. Yeah, so here's the fiber. And now I told you there are photons. I wanted to maybe just show you a picture of the photons because I think you've looked at photons in this class. So if we take a histogram and we have a detector for the photons and we plot as a function of time what's the probability that the photon arrives, then we get some distribution that looks like this. So we see maybe it's most probable that the photon arrives a few microseconds after we turned on our laser, and then the tail dies out by about 50 microseconds. So there's a couple things you might notice. If you're Pascale, you would look at this and say, oh my God, those are really long photons. Tracy, are you sure you didn't label that accidentally? No, so these are really microsecond long photons. If you calculate how many hundreds of meters those photons are spread out over, yeah, it's hundreds of meters, and which are much longer temporally than the photons that her quantum dots are generating, because they're generating photons that are much broader spectrally. So long photons in time, and also there's actually photons from both nodes that are on top of each other. One of them is orange, one of them is green, but you can't see it very well because they're overlapping very nicely with each other. So we've tried to make them look like each other, and they do look pretty much like each other. The other thing I thought I would show you if we want to compare the photons from the two nodes is a Hangu-Mendel has Hangu-Mendel interference, because you've seen that before. So this is looking at coincidences. So if we send identical photons from the two nodes and we send them onto a beam splitter, the blue case is when we choose them not to be identical because they have orthogonal polarization, sorry. The red case is when we choose them to be identical. And so you can see this dip in the middle is telling us, yeah, when they are identical, they actually are not arriving, or they never go to opposite ports of a beam splitter. They're always bunching, as the Hangu-Mendel effect tells us that they will. So this is verifying that, okay, it should work. These photons really do seem to match each other, so we can use them to entangle these two laboratories. So what does it mean? Here's this measurement that you've seen already today. Photons come in from one lab, from another lab. They go to a non-polarizing beam splitter that erases that witch path information. And then each photon goes out one of these outputs. We want to analyze the two photons, so we have two polarizing beam splitters. And so depending on the polarization, the photon will either go to the left or to the right, and that will tell us about its polarization and about which path of the non-polarizing beam splitter it came out of. So there's different possibilities for where we could detect two photons. We could detect, for example, one here and one there, and that tells us the two photons went out opposite ports. But it also tells us that they had orthogonal polarizations, because this photon went straight, and this photon had to turn a right angle to get to that detector. So it means they have two orthogonal polarizations, and that tells us that the atoms are also now in different spin states. And so this is, we started with, say, again, the ion in spin up, and in a horizontally polarized photon, or the ion in spin down in a vertically polarized photon. And we had that in both cases. And now what we've measured is one horizontal and one vertical photon. And so it tells us that either the first ion is spin up and the second ion is spin down, or the second ion is spin down and the first one is the first ion is spin down and the second one is spin up. And then there's a minus sign here. This is a so-called psi minus state. And we know that because of which of these detectors clicked, that we got clicks on opposite sides of our non-polarizing beam splitter. So this detection of the two photons, that tells us that we think we've prepared the ions in an entangled state. And of course, in order to publish this, in order to verify it, we should go back and measure the ions and show that we did it. And so this is what we do now. We get the two photon clicks, we measure the ions and check that they are in fact in this state. Before we measured the ions, we had to spend years doing a lot of other things, like synchronizing the timing between the labs, synchronizing the frequency between the labs, stabilizing the polarization along the fiber link. So this is a lot of work. I'm happy to tell you more about it, but I'll jump straight to the measurement now. So we think that the ions should be entangled. And a measurement is always just asking the question, is the ion bright or is it dark? And we use this laser that rotates us between our two qubit states to choose the basis of the ion in which we measure. So we can measure each ion in 3 different bases. And so whether it's bright or dark, we ask that question in 3 bases. So we do that for one ion, we do that for the other ion. That means there's a total of 9 different measurements. And that allows us to extract this so-called density matrix that describes everything we need to know about the 2 ions. And that also can tell us whether they're entangled or not. So the result of measuring the 2 ions, each in its own lab, a lot of times, every time we get the 2 photons detected. So we take all that data, and then we can use it to generate this matrix. And there's 2 important things about the matrix. One is the height of each of these peaks, and the other is that each of these peaks represents a complex number. So we're interested not just in its height, which is its absolute value, but also its phase, the phase between the real and imaginary components, and that's represented in the color. And so if we look at the height first, you see that most of the data is in the middle. And so this is when we're either one ion is in D and the other is in D prime. And so we have very little data where both ions are in one state, either D or D prime. That's exactly what we expect. It's not sufficient for entanglement, but it's what we need. And then if to demonstrate entanglement, we need to evaluate the phase here. And so this information with this matrix, we can then compare the matrix with respect to the target state, that up, down, minus, down, up, that psi minus state. And that calculation, taking the inner product of this density matrix with that state, allows us to determine how close we are to a perfectly entangled state. And this is well above the classical limit. So we know that if we didn't have this quantum mechanical state, if we didn't have an entangled state, we could never have an overlap between the ideal case and our actual case of better than 0.5. But we get an overlap of 0.83. It's not perfect. Perfect would be 1. But it's far enough above 0.5 to tell us that this was really entangled. That was the example where it was this state psi minus, up, down, minus, down, up. That's because we had clicks on 2 opposite sides of the beam splitter. There's also the case where we can get clicks on 2 opposite sides of the same polarizing beam splitter. That is, both photons went out the same output of the non-polarizing beam splitter. And that corresponds to the state psi plus, up, down, plus, down, up for the ions. And we can evaluate a separate density matrix for that. So you can see that the heights look about the same, but the colors are different. And the colors tell us about phase. And we can, again, evaluate the overlap and see that it's well above classical, that it's definitely entangled, because 0.88 is much greater than 0.5. Right, so that's what I wanted to tell you about this experiment that we did in our laboratory, again, together with my colleague, Ben Lannon. We published it a couple of years ago. But to wrap up in these last 10 minutes, let's think about how we could scale up this system. So linking together 2 ions, it's really fun, but it's definitely not a quantum internet. So the next thing we know how to do is to go from 2 to 3. And so we would like to connect a 3rd node that's in my lab here. This is another camera image, and you might see it looks a little bit different than these 2. It's actually a lot smaller, which you can't see from the picture. So here's sort of a cartoon drawing of it. And the point here is that this is an ion trap. It's a very different kind of ion trap. It's cut out of actually a diamond wafer, but the cavity is actually a really different thing, because here, these are little optical fibers, and the cavity mirrors are on the tips of the optical fibers. So the mirrors I showed you before for the optical cavity, they were about 1 centimeter in diameter. It's, again, something you could hold in your hand. These are tiny little optical fibers that are just about 200 microns across. So we're trying to build here a very tiny little cavity that we couple the ions to. And one reason to do it, let's see. So here's some more pictures of it. Yeah, this is like a little mirror on the tip of an optical fiber. And this is showing that we can bring the 2 mirrors together to make a cavity. And so the ion trap design is based on a design that is developed by the National Institute of Standards and Technologies in the United States. And the fiber mirrors, these were really pioneered here in Paris by Jakob Reichel's group. And so these mirrors that we have are a collaboration with Jakob's group at ENS, where students came here to Paris and fabricated the mirrors in his group. And so it's really a beautiful development that then allows us to build these very tiny little cavities. Why are we trying to make them so tiny? So one reason is so that the mirrors don't bother the ions too much, because the mirrors are big pieces of glass. It's a bit disturbing for the ions and the electrical fields. And so if we can make them really small, then hopefully if we can make them small, we can actually bring them closer to the ions without causing any problems. The reason we want to bring them closer to the ions, we can have these very short photons. So instead of now those long photons of kind of tens of microseconds, this is now a photon with about like 200, 300 nanoseconds long that we've generated in one of these traps. This is from a PhD thesis in my group from 2024. So these photons are temporally very short. That would be kind of nice for quantum networks, because they would be coming out of your system a lot faster so that you could use them for something practical. It also means that interaction between the ion and the photon, this is this coherent interaction between light and matter, this will now be faster than the decoherence rates of our system. In particular, the main sort of decoherent villain here is spontaneous emission of the atom. And we want to try to beat that rate with this coherent interaction. OK, so this is one thing we could do. We could try to, we've built this other node. We could think about going from from 2 nodes to 3 nodes. We actually have a 4th node that we are building or have actually recently completed together with Alpine Quantum Technologies, and that's up and running. So we would like to connect that in a network so we can sort of start adding these nodes together. But I showed you this picture here of this vision of this is now what? Something like 10 nodes connected together, 9 nodes. And nobody is doing experiments with 9. Nobody is even doing experiments with more than 3. So, right, does it make sense to keep adding nodes? And so the point I want to make is that actually only 3 research groups so far have demonstrated remote entanglement of 2 systems. That could be ions, could be NV centers. Actually, the research groups so far were 2 ion experiments and 1 NV center experiment, faster than decoherence at each node. Actually, yeah, so I think it's actually 4. I think there's 3 ion experiments and 1 NV center experiment. Right, and so what does it mean? It means that each node, you're storing information, and it's falling apart while you're trying to entangle it remotely. And so if it's falling apart, if your decoherence is faster than you can generate remote entanglement, then it doesn't really make sense to try to keep adding nodes before you can solve that problem. Because you're only going to be able to work with a useful network if you can entangle remote nodes faster than they fall apart. So what I want to emphasize is that in order to build useful quantum networks, it's not only important to sort of add more nodes, but also to speed up the entanglement rate and also to increase the coherence time of your system. And so all 3 of these things are important: the number, but also the speed, and finally the coherence time of the system. Okay, so I described to you linking together 2 ions across a university campus, something like half a kilometer of optical fiber. That worked pretty well for 854 nanometers of fiber, because losses kind of start to kick in for that wavelength at about a kilometer. So it wouldn't work so well for more than a kilometer. And if you start to talk about tens of kilometers, now you really need to be at telecommunications wavelengths of like 1,300 nanometers or 1,500 nanometers, 1,550 nanometers. You heard about this today at the end of the lecture, and so this is, I hope, a reminder of what you saw about an hour ago, that this is our vision, right, to connect these 2 experiments over much longer distances. We would still keep them in our labs, but we can just use a fiber spool with 50 kilometers of fiber and put it in between. And the way to do that is via quantum frequency conversion. It's by taking our photons that are at this infrared wavelength, that's the native wavelength of the calcium atom, and converting it to telecommunications wavelength. And this is something that actually my colleague Ben, who's working on the second experiment, his group has really focused on. And so this is from one of his papers. You can see that cavity ion system above. It's a sketch of the one here in the lower right. And here's the calcium level diagram that I described to you, how single photons are generated in the cavity. And then here, as you can see in this illustration, it's a single photon leaving the cavity, and then it's going into 2 different crystals of periodically poled lithium niobate for this nonlinear process. So it's a single photon, goes through these crystals, and then a strong pump laser at 1900 nanometers comes in, and the idea is to convert the single 854 photon to another single photon, but at our target wavelength, which is 1550 nanometers. And so, yeah, amazingly, you put in this 1 photon at 854, you put in a strong pump laser field, and just 1 photon comes out at the wavelength you want at 1550. The reason there are 2 crystals is because each crystal handles one of the 2 possible photon polarizations. And amazingly, the photon is still entangled with the ion. So if you start with an ion entangled with an infrared photon, you put the photon through this process, the photon is still entangled, the new telecom photon, it's still entangled with that photon here in your trap, and that's what my colleagues have shown. Right, and then the beauty of this quantum frequency conversion is that you it wouldn't even have to be ions. You can start to link together to build hybrid networks and link together very different systems because you can convert everything to telecom. So it doesn't matter if your different systems have different wavelengths. Right, just to wrap up, 2 very quick slides to show you that, to point out that quantum networks, it's not just about these, the physical hardware of what we're testing in the lab, but there's sort of a whole vision of a stack, a full stack approach that it's important to, in the end, we expect for these quantum technologies, there's going to be some user who's working with software. They want to implement some application. And then our physical hardware is way down at the bottom, and they never interact with it at all. So we did some work recently, or we published work recently that was done some years ago on working with with our collaborators from a number of groups, including a couple of groups here in Paris, and led by Delft, about a full stack approach, and in particular an operating system for quantum networks. So the Delft team really wrote this operating system for quantum networks, and then we tested it. So they tested it on one platform, this nitrogen vacancy center platform. And the idea is that this is an architecture that executes quantum network applications in platform-independent high-level software. So we wanted to test it on different platforms to demonstrate that it really was platform-independent. Delft specializes in nitrogen vacancy centers, but this here is the little ion trap that I showed you before. And so we tested this operating system with our ion trap. So that's the vision, operating systems, not just hardware. But for now, yeah, what I focused on today is the hardware. I showed you that we've entangled these 2 ions. And to wrap up what I've showed you, I hope I've convinced you that this ion-photon entanglement can be a building block for entangling ions over long distances, that these cavities offer us efficient collection and control over coherent dynamics in quantum interfaces. And that when you detect 2 photons, what we saw today is that this heralds remote entanglement between spins. Here they were ions. And right, a route to scaling up these systems means we need faster entanglement, longer coherence times, and more complex network structures. And a lot of people are really engaging with these challenges worldwide. Thank you very much. And let me show you the people who worked on this topic. These are the people in this publication from my group and collaborators from Ben Lanian's team and also from Nicolas Sangard's team now at CEA, then in Basel. Thanks.